So today we're dealing with oxidation reduction, or also known as redox. And the reason why they call it redox is there's your reduction, there's your oxidation component there. And the sad thing is you've already been doing this, you just haven't realized it. And this is what happens in every single replacement reaction. There's an oxidation and there's a reduction reaction taking place. And today what you're doing is you're actually dissecting that single replacement reaction and telling everybody who's being oxidized and who's being reduced. Now, I don't believe there's any blanks on here, and I'll do that demo or something similar to that here in a moment. All right, so what I want to go to is this statement right here. It's called Leo says grr. I don't know if you've heard this before, or maybe you may have heard oil rig. Okay. Have you guys ever done redox? Okay, good. Okay. That's why I'm doing this. All right, so this is how you can remember, and there's two. I've got Leo says grr or oil rig. I don't care which way you remember it. But with Leo, it's lose electrons is oxidized, or an oxidation. Now, we talked earlier in the year that who loses metals? Who loses electrons? Metals or non-metals? Good. So when we talk about a metal losing electrons to give it to its non-metal, it's actually undergoing oxidation. So it's becoming what? More positive or more negative when it gives away those electrons? More positive. And so if somebody's giving away electrons, something else has to take those electrons. And that's what this is. Gaining electrons is reduction or reduced. So you have to have somebody that's willing to give away the electrons, and you have to have somebody that's willing to take those electrons. Now, oil rig is oxidation is losing electrons. Rig is reduction is gaining. Same thing. Same principle, just another way to think about it. Okay? I hate to ask this question because inevitably I always get a strange answer. But when you see half reactions, how many half reactions can you have in a whole reaction? Hey! All right. So no, we cannot have 3 half reactions in a whole reaction. So when we do net equations for redox reactions, it sounds intimidating. It's not that bad. It really isn't that bad.
I feel like you're lying.
I can't lie to you. I won't lie to you. Now, hang on. Shh. So here is an example of what we're going to do, and I'm going to do quite a few examples. Oxidizing agents. You may want to highlight this. Okay? It's right underneath this. We're going to talk about the agents when we do the example, but the agents allow the other thing to happen. That's what we're going to find. See all the suspense? This is better than any action-packed movie. Let's do an example. Oh, let's do a demo first. So we have this reaction. Now listen. Shh. We have this reaction up here where it's iron plus copper sulfate. And what kind of reaction is this again?
Single replacement.
Very nice. Very nice. You should know this. This is one of the 5 reactions. All right. So in this case, attempt to replace the copper and kick it out. So what products will we have on the other side? Fe with the sulfate and copper. Now listen, guys. Thank you. So in this case, a single replacement reaction, things that we've been doing for the last couple of days, this is the reaction that's taking place. Now, when I were to ask you, what is the charge on iron all by itself here? 0. Very good. What's the charge on copper here? What's the charge on sulfate? Let's start there.
-2.
So copper has to be a +2. Okay. Over here, what's the charge on copper? Nothing, because it's all by itself. That's really important to know. And what's the charge on the iron here? +2. So what's happened is the iron has gone from no charge to a +2 charge. And then the copper went from a +2 to no charge. By just looking at this reaction, who is being oxidized? And what's oxidized mean again?
Copper.
Losing electrons. That's Leo. Leo says grr. Losing electrons is being oxidized. So who's being oxidized? Very good. Iron, because it has all of its electrons, and it goes to a +2. Then going the other way, the copper goes from a +2 and it gains 2 electrons and becomes more negative. Well, in this case, it becomes 0. So the copper is being reduced. Okay, and we'll do some half reactions to represent this. But what I have here is I actually have a iron nail. Okay, and it kind of looks silvery to you. Okay, kind of see that shine, that glitter. And if you look at the periodic table over there, most of the metals are what color? Silvery in color. Okay, so if I were to take this iron nail that has, what are the charges on all these iron atoms? 0, very good, because it's with its own kind. Remember that. And I were to place it in this solution of copper sulfate, which has copper ions and sulfate ions in it, in a matter of a few seconds, it changes into copper. Okay, I'll show it for the camera. So what's happening is that the iron is replacing the copper ions, and the copper is coming out of solution to form pure copper. Chemistry. Boo. All right, so here are the half reactions that I promised you. Okay, so one of these we're going to have iron with no charge going to iron with a +2 charge. Okay, what did we say happened? Did it gain or lose electrons? Very good. So that means if it loses electrons, we put it over here. Because on this side, it has all of its electrons. Here it has 2 less. Where'd they go? Somewhere. Very good. That's a good question. So we have to look at who our somewhere is. So we have copper with what charge? +2 goes to copper. Whoa, that's cobalt. Goes to copper with no charge. So how did it go from +2 to no charge? Gain 2 electrons. Very good. So these 2 electrons, which are here and here, are these the same electrons?
Yes.
So in other words, the iron is losing 2 electrons, so the copper can gain those 2 electrons. That word Fe? We're not going to have an Fe here.
Okay. So if Fe plus copper.
Can we do some more examples?
Yeah.
Okay. Now, yes, Adam.
I don't know if this is a dumb question or not, but so could pennies originally be silver and turn to copper that way?
No. Because notice that the copper is still copper on this side and this side. So what's happening is you might be looking at this going, well, where the heck is a solid copper? It's an ion. And that's what all this blue is. That's what copper with a +2 charge looks like. It's that blue color. And then when we pull it out, it gains electrons and changes back into its normal copper, which is kind of cool. Wow.
Are we allowed to drink that?
No. Go ahead, Hunter.
Okay. So if you stuff this in there for like a long time with more copper build up on it.
Yeah, and I'll do that at the end of the day. It gets kind of nasty and grungy. Yeah. I don't know if it's sweet, but yeah, it's nasty looking. I actually have to sacrifice a beaker when doing that because that whole reaction's just nasty.
It's worth it.
All right, forgot to ask. Who is oxidized in this reaction? Let's be formal on this. The iron is oxidized. Very good. And who is reduced? The copper. Now, as a heads up, only reactants can be oxidized or reduced. So everybody hear that? What'd I say, Hunter? Only reactants can be oxidized or reduced. So I may ask on the test who is oxidized, and I'll give you the possibility of iron, no charge, copper with a +2, iron with a +2, or copper with no charge. So you can automatically eliminate these two options because they're on the product side. So then you boil it down to these two, now you got a 50-50. But if you know who's doing what,
Can you say the question again?
I said only things that are oxidized and reduced can be on the reactant side. Okay, yeah. Also, here's how we do agents. Okay. If I am looking to find who the reducing agent is, I need to find something that allows for something else to be reduced. So when iron goes from a no charge to a +2 charge, it loses 2 electrons so that the copper can gain those electrons. So iron, even though it's oxidized, it behaves as a reducing agent to allow copper to accept those electrons. And remember, if you don't have something that can accept those electrons, it can't lose those electrons. So if it's just iron all by itself, let's say we're just looking at that iron nail. It's been sitting in the box for about 5 or 6 years now, waiting for an opportunity to do something. Okay? And until it actually has that opportunity, it's not going to do anything, sadly. So here's an easy way to remember it. If it's oxidized, the agent is the opposite name. So what do you think is copper +2? It's what kind of agent? Oxidizing agent. Very good. Because having the copper +2, it allows or it permits the iron to lose electrons so that it may gain those electrons. Okay. So the hardest part of this is figuring out who's oxidized and who's reduced. And if you have electrons on the product side, then you're losing electrons. Okay. And if you have electrons on the left side, then you're gaining electrons. Now keep in mind, you can never have two half reactions where the electrons are on the same side, whether the reactant side or the product side. They have to be on opposite sides. Somebody has to gain, somebody has to lose. Yeah.
So is the green ink a half reaction and the blue ink a half reaction?
Very good. So when we combine those two, we have a whole reaction. Sandpaper. Okay. All right, let's do another example. Here's our practice problem. Okay. We'll do, I know there's like 4 practice problems. I'll do 2 and I'll have you do 1, then we'll do oxidation numbers. Say that again, I'm sorry.
So like the example we're about to do.
Oh, you mean here? Oh. What I'm not showing is the non-metal. Notice I had the sulfate in here. So I just left the non-metals out. Because what happens to sulfate? Good question. What happens to the sulfate from the reactant side to the product side? Nothing. It just stays the same. It's not gaining electrons. It's not losing electrons. It's allowing for the non-metal to say, hey, come on over here. Or the metal to, come on over here. Be with me for a little while. You know how it is. Yeah. And if they don't, then we bounce charges. All right. So here, this is typical of what you'll see. So let's write the 2 half reactions. And it doesn't matter which one you start with. Do you want to start with the lithium or the lead? Okay, that's fine. So I'm going to, let's use a different color. Yellow's that. All right, so lithium. And notice it doesn't have a charge. If you choose to write a 0 or leave it blank, it's fine. I'm going to write a 0 just to indicate that there's no charge there, especially since we're doing something that involves charges. So lithium goes from no charge to a +1. How did it do that? Did it gain or lose an electron? Lost an electron. And if it loses, it's over here. So keeping in mind, lithium has all 3 of its electrons here. Over here, it has lost one of the electrons. Now it only has 2. That's why it's a +1 charge. And there's that 1 electron. The other thing, lead +2, okay, goes from +2 to lead. So in this case, did lead gain or lose electrons? It gained. It went from a +2 charge, and when it gains electrons, it becomes more negative. And in this case, it's neutral, but that's still heading toward the negative end. So it gained 2 electrons. Uh-oh. We have 2 electrons and 1 electron. So, and remember, I can't give away just 1 electron and lead go, okay, it's okay if I go from a +2 to a +1. No, it's gonna go full throttle, all right? So how many electrons or how many lithium atoms are we gonna need for this to be satisfied? 2, that's balancing the reaction. So in this case here, we're going to double the top because, let me ask you this. How many balanced equations have you seen in your long lifetime that's had electrons in the final balanced equation? 0. And you're not going to see any starting today because we never show electrons because we always balance it out. So in this case, how many electrons do I have on the right side? Or actually, let's do this. Let's bring everything down here. Let me scoot you down here. Okay, so what I'm going to now do is I'm going to rewrite this as 2 lithium and 2 lithium plus 1. You don't have to do this, but I'm going to show it for today. And 2 total electrons. And let's go ahead and put the 2 electrons for the lead. Again, rewriting this just for clarification purposes only. Okay, so in this case here, if I look at my 2 half reactions, they have the same number of electrons. If you have the same thing on both sides of the arrow, treat the arrow as an equal sign, cancel it out, and then bring everybody down. So in this case, our final answer will be 2 lithium with no charge. Add that to a lead with a plus 2 charge, 2 lithium with a plus 1 charge, and lead with no charge. When we finish, we have to make sure we have the same number of atoms on both sides, and the charges have to be the same. Not 0, they have to be the same. So what's the total charge on the left-hand side here? We have 0 plus 2, so that's a total of a plus 2 charge. Here we have 2 times plus 1, which is plus 2 plus 0. So the charges are the same. That's the first check. Next check, I have 2 lithiums, 1 lead, 1 lead. I'm good. We didn't do that for the first one since they were 101. Okay. So what I would ask, here would be a good test question for Friday. Okay. You would be given this right here. Okay. That's what you'd be given. And I might ask, who is the oxidizing agent? And it would be wise of you to actually go through the process and then identify. So first of all, who is oxidized in this reaction? Lithium, this right here, is oxidized. And who's reduced? The lead plus 2. So remember, only reactants can be oxidized or reduced. So that's our reducing. The lead is reduced. So who is my, what did I ask, reducing agent or oxidizing agent? Oxidizing agent. So who's my oxidizing agent? Lead plus 2. Okay. That's how you would answer a question like that. Then I may ask, how many lithium atoms are there in the final balanced equation? Hopefully that wouldn't be too difficult, even if you knew how to do redox or not.
So the one gaining is the one that's oxidized?
Correct. Think of it like this. Ask yourself, who's oxidized? It's the reducing agent. Who's reduced? Oxidizing agent. So it's always the opposite. Because the lithium allows for the lead to be reduced. That's why it's the reducing agent. And then the lead allows the lithium to give away its electrons. That's why it is the oxidizing agent. It allows for that change to occur. Let's do another. Because it's so dang easy, I know.
Nope, that's definitely not one.
I know you're yelling, challenge me, it's so easy, please.
That is the farthest you could possibly get from this.
It's only chemistry, come on.
It's only chemistry.
All right, so which one do you want to start with? The chromium plus 3 or zinc?
Zinc.
Zinc it is. So we'll go zinc, and if you want to start with chromium, you could do that. It's not going to change anything. Your notes don't have to look like my notes. It's all right. All right, so is zinc being oxidized or reduced? Oxidized. It's becoming more positive. It's becoming more positive because it's losing electrons. So what is the chromium doing? Or, I'm sorry, chromium plus 3. There we go. So it's going from, and I didn't put the charges on there, but again, that's optional. So in this case, how many electrons does it gain? Has a +3 charge. So if it goes from, and always look at the charges. It goes from +3 to no charge. Oh, sorry, wrong one. All right. So, do we have the same number of electrons on both sides? No, we do not. So we need to multiply the top by 3 and the bottom by 2. And if you need to rewrite it, not a problem. You did. It's all right. So 3 zinc with no charge plus 6 electrons plus 2 chromium plus 3 makes 3 zinc plus 2 plus 2 chromium, no charge. And how many electrons on this side? Very good. So what happens to the electrons? Get them out. They're the same. We're not going to have ever, I don't care if you go to AP, if you go to college, you're never going to have electrons in final equation. What's that? I put them there just to show you that they're going to cancel because some might not be able to see 2 times 3 equals 6 or that 3 times 2 equals 6. So I was being a nice guy. You're welcome, Brock. You're welcome. So what remains is, and if you need to rewrite it, again, it's so much fun to write these. It's like the best thing ever. They're so dang easy. Some of you are going to grow up to be a chemistry teacher. You're going to go, I'm going to remember those days. All right. So here's the question. Who is my reducing agent?
Would it be
So it's right there. Zinc with a +2 charge? Again, it has to be on the reactant side. So it's zinc with no charge. Why? Because zinc is being oxidized, so the agent is the opposite name, reducing agent. Go ahead. Go ahead, Joanne. No, you can figure it out at any time. That's just when I ask. And Brock, if you need to rewrite it, you may. Yeah, Cameron.
So what was the exact question?
Who's the reducing agent?
So 2Cr plus 3 would be the oxidizing agent, right?
What'd you say? Who would be the reducing agent? Zinc +3? Is that what you said? What'd you say?
I said, or at least I think I said 2Cr plus 3 would be the oxidizing.
Oh, yeah. I'm sorry. It'd actually just be, the oxidizing agent would just be the chromium +3. The balancing, that's how many we have, but it's the chromium. So the reducing agent really is the zinc. Sorry. You don't include the coefficient.
So the reducing agent is always on that side.
Always on the left. Yeah, Julianne.
So whatever's being oxidized, that's the reducing. Wait, did you say the reducing agent is always on the right side?
Yeah. Makes it so easy. The agents must be on the left side. And who's oxidized and who's reduced must be on the left side. I'm going to record. I'm going to count how many times I said that in this video. Correct. But they're not the same thing. One's a reducing agent, one's an oxidizing agent. One is reduced, one is oxidized. All right, try number 3 on your own. And the question I'm going to ask here is, who is the oxidizing agent? Now let's see how good you are. Can you figure it out by just looking at the equation?
Is that it? Yes, you can. Is that all you're asking? Or like,
That's what I'm asking.
No, it's
Oh, you
iron.
should have
Iron.
first.
Iron's the
Thanks.
Ah.
It's iron.
Now, work this out. Work it out. Don't look up here. But I just gave you the answer. Or actually, sorry, Kate gave you the answer.
I know. I don't think there's.
Now, this one, I'll admit, is not as romantic as the others. I apologize.
None of these
Oh. Some of these are just drop dead gorgeous. It's hard to believe.
You're
What's
funny.
gonna be the format of questions?
Ask that again.
The format in which you ask like questions for these types of
Question.
problems.
Yeah. I just did it.
Just oxidizing agent.
Yeah, who's oxidized, who's reduced, who's the agent.
Is it really gonna go down to like actually doing all that extra?
For some, it may. Hey now. Isn't that an exciting reaction? You guys do it.
They're gonna be concepts on the test, or
Yeah.
is it just like this?
That's a concept.
No, but like actual like questions, like
Yeah, that's a concept.
no.
It takes a lot of thought
So
and.
like direct questions. Like, what is this? And then you have to answer it. Like
You mean vocabulary?
yeah.
No, that's not a concept. That's a regurgitation.
It wouldn't have been any better.
Yeah. Yeah, no.
So why is that the oxidizing agent at the top? But what do you call magnesium at the bottom?
What do I call this?
Like, at the beginning you call magnesium for reduction.
It's a reducing agent.
Yeah.
Is that what you're asking?
Yeah, but at the very end, iron. Correct?
Say that again.
At the end of the
Hang on, guys. Hang on. Shh.
At the end of the problem, when it says Fe plus Mg plus 2, isn't magnesium the oxidized?
It's being oxidized, if that's what you're asking. It is oxidized while the iron plus 2 is reduced. Is that what you're asking?
Yeah.
Okay, that I like. That's dead on.
I was just trying to tell the difference between the oxide at the top and oxide at the bottom.
Okay.
Yes. Yeah, I got it.
Yes, Cameron. Oh, it's soaking in. It's I'm sorry, it's marinating.
Wait, okay. So
Come on, get it out. I got more.
you said that
Oh, God.
that the is always on
They're always on the left. Notice that I have left,
all of that is
left, always on the left.
I know, but isn't oxidation on the right?
The electrons for the oxidation reaction are on the right. Those are electrons.
Okay, so then the oxidation is always on the left too.
Yeah.
So those are always
Yeah, always on the left. All right, Hunter.
Okay, so iron is being oxidized.
No, iron is being reduced. Therefore, it is the oxidizing agent. It's left. Sometimes it turns out to be the same. Sometimes it does not. Got it. All right, now let's look at. Now, hang on here. We got more. All right, oxidation numbers. Okay. Now listen. We only have 10 minutes. Shh, please. We're done with oxidation reduction. Determining oxidation numbers. Now, we've talked about oxidation numbers in the past. Now we're going to talk about those oxidation numbers that you've been looking at for a while going, not nickel, but nitrogen's got like a +5, a +3, and other charges on there. This is why. Some were asking, how in the world does phosphate have a -3 charge? Well, here's the reason why.
Yes.
When figuring these out, here's the best way, because I'm going to ask you, what is the oxidation number for a particular element? When you have a compound like this, sometimes it's easy, sometimes it's not. I like doing this method. Oh, let's use this color here. Sorry. So I like to line them up. So I've got sodium, phosphorus, and oxygen. And it's kind of a modified inventory. How many sodium atoms do we have? 3. Good. How many phosphorus? 1. How many oxygen? And what will the charge on oxygen be every single time? -2. Always. Always, always, always. So if I have 4 oxygens and I multiply that by -2, that gives me a total charge of -8. What is the total charge on the sodium phosphate? The total charge. Algebraic sum equals 0. Very good. It's always going to equal 0 for what we're doing. So we want to make sure that all of these numbers that we find equal 0. What's the oxidation number for sodium? And it only has a single oxidation number. +1. Good. So we're going to do +1 times 3, which gives us a +3 charge. Now my question is, what is that mystery number that when you take +3 minus 8 plus the mystery number that will give us a 0 charge? A +5 or -5? +5. So if I put a +5 in there, how many phosphorus atoms do I have? So 5 divided by 1 is still 5. These are the oxidation numbers. Now, as a check, you always want to go back to your periodic table. And I only have it in unit 7. So when I look at, say, phosphorus, see if I can zoom it in, get it over there. Okay, notice the charge on phosphorus can either be +3, -3, or 5. And in this case, we had it as a, what charge? 5. So that's a good number.
Does it matter which one you do first?
I would recommend doing the oxygen first.
Is there always?
There's always going to be this mystery in the middle. Okay. Let's do another. Okay. All right, let's skip the CuSO4. Everybody knows that one. We're going to show you another one. All right, so same thing with the nickel phosphate. Okay, so line them up. So we got the nickel, we got the phosphorus, and we got the oxygen. How many nickel atoms do we have? Very good. 3. How many phosphorus in this case? 2. Very good. How many oxygen? 8. And all of these will add up to 0 because algebraic sum equals 0. Now, nickel, interesting. Let's skip that for a second. What's the charge on oxygen every single time? -2. So we have 8 of those times a -2, which gives us a -16. Remember, that's the oxidation number. This is the charge on the atom. Here, let me speed that up a little bit. Sorry.
Oh, okay. The oxidation number for oxygen is always going to be -2.
Yeah, it's always going to be -2. Okay, so.
So you just have to get the other 2.
And then we have to get the other 2. Now, here's the crazy thing. Nickel can either be a +2 or a +3 charge. So we're going to let the non-metal tell us what the charge on the nickel is, like what we've been doing. So what's the charge on phosphate here? -3, very good. And how many do we have? 2 of those. So that's a total of -6 from the non-metal. How many nickels do we have? 3. So what must the charge on each nickel atom be? +2. So that gives us a total charge of +6. So what is our mystery number here? 10. Very good. 10. So when I do 10 divided by 2, what is my +5? The numbers in the box are your oxidation numbers. These are just charges that help us get the oxidation numbers. So if I were asking you what the oxidation number is, and trust me, on the test, I'll throw in some, like a +10 for your phosphorus. If it's not on the periodic table, I promise you it's not an option. All right? So if you're like, oh, but I have +10. Okay. How many do you have? Make sure you divide it by that. Okay. Let's do another one. Silver iodide. So your homework for tonight, and I know some of you are like, oh, this is so easy, I want to get started, is the Redox worksheet. And you know who you are. See, Cameron's already leaving. Perfect. All right, so silver iodate. So we're going to start off with silver, iodine, and oxygen. How many silver atoms do we have? 1. And how many iodine atoms? 1. How many oxygen? 3. And what's the charge on every oxygen? -2. So you better not miss what an oxidation number for oxygen is. So -6, and all that equals 0. Now, silver only has a single charge. Anybody remember? +1. Good. So what is our mystery number here? 5. Now, don't get in the habit of thinking, oh, our answer is always going to be 5. That's just the coincidence that we've been doing here, so I apologize for that. For those of you who become very robotic in your methods. Okay, so there are our oxidation numbers. As a quick check, always check your periodic table. So let's go find it if I can. Daggone it.
So finding the oxidation is all you'll be doing today?
Yeah.
Or are you going to add something tomorrow that completely makes me hate it?
Well, yeah, this is the last lesson. So the options for iodine, +1, -1, +5. There we go. Yeah. Always get a periodic table. Yeah. All right, so again, the homework for tonight is the Redox worksheet. So work on that. Wasn't that a fun last lecture? Oh. Thank you, Kay.
Yeah, the second part was fine. The first part was.
Please, it's all fine. Thank you. So
Your computer's in the way. I did not see any.
Yeah, you should move the thingy.
it's now coated with copper atoms.
That's true.
Wait,
You should do that again. Yeah, but I want to see you do
Burn the witch.
Why would you want to do that?
Well, maybe I wanted to see it.
It's not magic. It's chemistry. So we have, in here, we have the copper ions, which are blue in color. And notice that it's silver. And when I place it in, it's spontaneous. Oh, wow. Well, leave it in for a few more seconds.
It turns into rust?
No. Copper.
See?
Water.
Will it like rub off with a nail?
It's copper atoms. I'll have to sand it.
Can I touch it?
Okay.
What happens if you put your finger in?
Turn your fingernails blue. You have
Is it
cuticles.
really?
Yeah. Yeah, you don't. It's a nasty blue. So I try to keep it because my fingers are so beautiful. But so what's happening is that the iron is replacing the copper ions, and the copper is coming out of solution to form pure copper. Chemistry.
I'm the one wearing all gray. Honestly, I kind of want to watch demonstrations.
Boo. Remember that. And I were to place it in this solution of copper sulfate, which has copper ions and sulfate ions in it. In a matter of a few seconds, it changes into copper. Okay, I'll show it for the camera.
Your computer's in the way. I did not see any.
Yeah, you should move the thingy.
So it's now coated with copper atoms.
That's true.
Wait,
You should do that again. Yeah, but I want to see you do
Burn the witch.
Why would you want to do that?
Well, maybe I wanted to see it.
It's not magic. It's chemistry. So we have, in here, we have the copper ions, which are blue in color. And notice that it's silver. And when I place it in, it's spontaneous. Oh, wow. Well, leave it in for a few more seconds.
It turns into rust?
No. Copper.
See?
Water.
Will it like rub off with a nail?
It's copper atoms. I'll have to sand it.
Can I touch it?
Okay.
What happens if you put your finger in?
Turn your fingernails blue. You have
Is it
cuticles.
really?
Yeah. Yeah, you don't. It's a nasty blue. That's why I try to keep it because my fingers are so beautiful. But so what's happening is that the iron is replacing the copper ions, and the copper is coming out of solution to form pure copper. Chemistry.
I don't want to wear all gray.
Honestly, I don't want to watch demonstrations.
Boo.